All right, so now let's dive in. So as a quick recap of what we've done so far, we've looked at a few different types of generative model families. And in particular, we started by looking at different issues in terms of how we represent generative models. And by that, I mean, how do we define a probability distribution that serves as a model of the data that we have? And the first set of lectures looked at this question of representation from the perspective of latent variable versus fully observed models. So we started with a fully observed family of models, which were autoregressive models. And then we defined this new task of representation learning, and we defined latent variables or late variable models as one way of doing that. Then most recently in the, well, I guess starting in our lectures on latent variable models and then continuing into the most recent week, we looked at different learning objectives and different learning algorithms for these model families. Initially, with the fully observed models, we could optimize the likelihood directly in a way that's very straightforward. It's easy. But when we introduce latent variables, then we start to require approximate methods. And in particular, we looked at one important type of approximate learning technique called variational inference. So variational inference is a way of approximating marginal likelihood. But then in the next, in the last two lectures, we saw that maybe maximum likelihood is not the objective that we really want to use. It sometimes involves intractable integrals, or it involves intractable computational tasks, which is why we had to rely on variational inference. And also, it doesn't even necessarily correlate with things like sample quality, which is maybe what we're most interested in. And then in, I guess, in response to this issue, we defined another framework, which were GANs, generative adversarial networks, which can optimize arbitrary divergences using a sample-free based approach, where we're only optimizing the model using samples drawn from the model, but we never actually have to evaluate the likelihood itself. So these are different dimensions along which we can place the generative models that we saw so far in the course. And in this lecture, we're going to see yet another approach to defining a generative model, as well as its associated learning algorithms. And this approach will center on a different dimension along which we can construct models. It will focus on what I'm going to call normalized versus unnormalized or energy-based models. So this is yet another dimension along which you can place different generative modeling algorithms. And we're going to explore it in this lecture. And I'll start by defining what it means to have an unnormalized or an energy-based model. This will be in contrast to every other model that we have seen before, which was what I would call normalized. Okay, so the plan for this lecture is going to be to first define what energy models are, and then I'm going to give you a few examples of these models. I'm going to show you ways of representing probabilities using the energy-based framework. And then the last half of the lecture will look at learning algorithms for these models. And in particular, I will introduce a new approximate learning technique called Markov chain Monte Carlo, which is going to try to achieve the same goal as variational inference, but it will take a very different approach to that goal. So it's a very different type of technique that can be used as a replacement for variational inference, but it's based on a completely different set of ideas. All right, so that's the plan. If you guys don't have any questions, let me start by explaining what is an unnormalized or energy-based model and why it might be interesting. So at a high level, a lot of the effort in this course has been on defining probability distributions. We've spent a lot of lectures on finding clever ways to define a probability distribution over some data set of x's, which can be high dimensional images or audio or any other data form. And there's two main properties that any of our probabilistic model has to satisfy. First of all, because it's a probability, obviously it has to be non-negative for every x, right? So a probability distribution will be any function p of x that satisfies these two properties. It's non-negative, and when summed over all the possible inputs, it has to equal 1. That's just the definition of a probability. And so far, every model that we have worked with has satisfied these two conditions. This sum to 1 property, clearly we know that it has to hold for any probability, and it's also really important. It's probably the most important. It's probably the most important of these two properties, because it ensures that when we do any sort of learning, when we try to maximize the probability of the training set, because we have a fixed amount of probability volume to work with, by maximizing the probability of the training set, we are making it more likely, and then all the other data points that are not part in our training set will become automatically less likely because the probability has to sum to 1. So this property is a key feature of any probability distribution. So maintaining these properties can be hard or can be easy depending on which property we're interested in. So coming up with a non-negative function, g of theta x, that is usually the easy part. Here is just a set of examples of models g of x that are non-negative, that satisfy the first criterion. So for example, if I just take any neural net and I square it, that will, well, by definition, always be non-negative. Or if I take the exp of any function f of x that's parameterized by a neural net, that will always give me a non-negative number. So this is actually quite easy. What's hard in defining a probability distribution is the fact that for an arbitrary non-negative g of theta, it might not necessarily sum to 1. It's actually much harder to get g of x to sum to 1 than for it to be non-negative, right? So the reason is that in general, there's not these non-negative functions that I just gave you as examples. There's nothing that forces them to be equal to 1. And so as a result, if I just use these simple examples, I don't get a valid probability. I can't really use it for generative modeling. So getting a normalized g of x is something that's not necessarily straightforward. In practice, what we have to do, and what we actually have done implicitly, is to normalize this g of theta by its total volume or by its integral, such that it does sum to 1. So we have to apply some kind of normalizing factor to an arbitrary g of x in order to enforce this sum to 1 property. And we have implicitly done that when we defined the different types of generative models that we have seen in previous lectures. So for example, when we define an autoregressive model, we're implicitly choosing a g of theta such that this volume or this integral is available to us analytically. So by analytically, I mean that we know what that integral is, and we can easily apply its normalization term, right? So in an autoregressive model, we have a joint distribution that's a product of terms, such that for each term, we know what is the integral. And then once we know that, we can ensure that the full distribution sums to 1, because when we have, so I guess if we have a joint autoregressive model over two variables x and y, its integral is given to us by this term. Then when we pull the inner integral inside, we know that this has to be normalized to 1. And then we get the marginal. The marginal will also integrate to 1. And we know that it always integrates to 1 because we're choosing these terms here to be some kind of conditional distribution for which we know the normalizing factor. For example, it's a conditional Gaussian, or it's a, if it's a softmax, then everything sums to 1 by construction in the softmax. So when we define our regressive models, we're always conditioning we're always choosing the conditionals to have tractable integrals here. And therefore, their product is also something that normalizes to 1. When we worked with latent variables, we assume that the P of x given z is also in some model family, again, like a Gaussian, for which the integral is tractable. Therefore, the mixture of these distributions will have, it will be normalizable in some form. So for example, if we were to do the full integral over all the x's and I have a mixture of 2 components, then that's just something that evaluates to 1. So again, with latent variable models, by construction, we always had components which integrated to 1. And then finally, when we work with flows, we had to, so we started with a simple distribution, and then we tracked the volume change using the change in variables formula. And that still ensured that after I apply the bijective transformation to my latent variable z, I still get something for which I can compute this normalizing factor efficiently. So in all of the, my point here is that in all of the modeling families that we have worked with so far, we chose the components of each model family. So each conditional in our regressive model, or the conditional in a latent variable model, we chose all of these probabilities to have tractable densities, to have tractable integrals. What I'm going to do in this lecture is try to get rid of this assumption and instead look at a more general class of models for which computing the integral is going to be not necessarily tractable, and I'm going to find alternative ways of enforcing this, an alternative way of dealing with this need of normalizing by volume. So what do I mean by that? So the idea of an unnormalized or an energy-based model is to parameterize distribution of the following form. In an unnormalized or in an energy-based model, I start with some model f of x, which gives me a score at each data point. I make this score non-negative by passing it via an exp. That satisfies the first condition for a probability. Now I have a non-negative score at each data point. However, these scores don't sum to 1, because in an energy-based model, I'm going to choose an arbitrary f of x. I'm not going to try to restrict this to any model family, at least initially. And the way I'm going to enforce that I have a valid probability is that we're going to try to normalize the function exp of f of x explicitly by adding the full integral over all the possible x's directly into the definition of the model. Okay, so previously we always chose a special type of model for which a special model family such that the integral of the generative model always evaluates to 1 or to something that we can tractably compute. Here in this lecture, in an energy-based model, I'm going to let go of this assumption, and I'm going to start by optimizing models with an arbitrary form, and I will ensure that they form a probability by explicitly maintaining and normalizing the distribution by this integral. And then to introduce some notation, this, as you can imagine, this term here is going to be very important. This is going to be the term that ensures that p of x integrates to 1. This integral is very important, and I'm going to give it its own letter, z, and z will be what I'm going to call the normalizing constant of the probability. So z of theta is going to be the number by which I need to divide my unnormalized probability to make everything sum to 1. And any probability that we can express in this form, we can call this an energy-based model. So an energy-based model is a probability of this form. That's the new type of generative model family that I'm going to propose in this lecture, and we're going to see how we can do useful things with this model family. Does anybody have any questions on the definition of an energy model, energy-based model? Jan.
My understanding is that we define a score function and then we softmax it to get a probability distribution. Is good? Because is it always, so are we going to have score functions that we can't softmax on, or?
Well, you can always softmax it on, theoretically. You can always define this probability. So first of all, when you say softmax, so normally softmax is something that is defined over a finite number of values, right? So if your x was discrete and if x would take a finite number of values, then yes, this would be exactly the softmax. Here, x can also be continuous, in which case the normalizing function becomes an integral. But I guess you can think of it as a continuous valued extension of the softmax. And then your question is, can we actually do this? Which is a great question. Well, in practice, doing this will be really hard, but we're going to see ways of getting around these difficulties. And the question of whether can we do it, we can always do it in theory. The question is whether it's computationally tractable or not. And there's going to be many cases where it's computationally intractable. And in those cases, we're going to rely on approximate methods. Okay, so yes, this constant here is really important. It's also known as the partition function. So it's the normalizing constant, also known as the partition function. And as you can see, it's a function of theta. So for each assignment of the model weights theta, we get a different score here. I'm going to give it a better name in a moment, but so right now I'm just calling it score at a high level. And this z of theta changes because when we change theta, we change the score. All right, so this is the partition function. You might ask yourself the question is, one question you might ask yourselves is, why do we exponentiate this score function? Why not, for example, take the square? So there's a few practical reasons. One is that typically probabilities vary a lot, especially when x is high dimensional. They could vary by orders of magnitude over different x's. And therefore, if f is on a log scale, right, because we exponentiated f is on a log scale, it's easier to model large variations in probability numerically. This model family, as I will explain later in the lecture, it generalizes other modeling families that you might be familiar with. Even a Gaussian could be placed in this framework, and many more. And there's also reasons that are based on theories from statistical physics and also information theory that explain why this is a reasonable, why the exp is a reasonable operator to use here. I won't go into these details, but there are arguments based on the principle of maximum entropy and also based on the second law of thermodynamics, which in a sense argue that using an exp here is the exp is the operator that when we use it, we end up making the least assumptions on what the probability should be given a certain set of constraints. I won't go into these details, but I can tell you more after the lecture, and I can point you to some readings. I just want you to be aware that there is theory from statistics and thermodynamics which explains why that's the case. And then one implication of this connection to thermodynamics is that we also often call this function minus f of x as the energy of the model. Again, this comes from the connections to thermodynamics. This distribution is called the Boltzmann distribution in physics. It's used to model the state of a system. And then this f of x can be thought of as the energy of a system. So in machine learning, we also refer to minus f of x as the energy. And this is why we call these models energy-based models. Okay, so here on this slide, I define what an energy-based model is. Now, why would we want to work with generative models of this form? The main reason is that it gives us very high modeling flexibility. If you remember, in most of the lectures, in most of the previous lectures, we spent a lot of effort trying to devise a careful type of probabilistic, we try to carefully derive a certain probabilistic model for which the representation would be tractable, right? So in an autoregressive model, we had to think a lot about how we define the conditionals. In a flow model, we had to spend a lot of energy to define a certain bijective function between z and x. Here in an energy-based model, we make the least set of assumptions. In fact, any neural net or any parametric function approximator can be used to define f of x. And then as soon as we have an f of x, our formula here gives us a valid probability distribution. So the main benefit of the energy-based framework is the extreme flexibility in terms of which representation we can use for our probabilistic model. However, as you can imagine, and as Jan alluded to moments ago, this is also going to be challenging from a computational perspective. At least without any approximation tricks, this is going to be difficult. And the main challenge here is going to be, as you can imagine, is going to be to compute this constant z of theta. This is going to be, computing z of theta will involve solving some high-dimensional integral, and we know from our lectures on variational inference that in general, this is hard and computationally intractable. So as a result, a lot of the standard things we like to do with generative models will become much more computationally difficult. So sampling is one such thing. Even evaluating the likelihood, and then as a result, optimizing the likelihood, these tasks are difficult because just to evaluate the likelihood, I need to compute this function z of theta. And also in its current form, this doesn't involve any feature learning, which is something that we also want to do. And okay, there is a question. By the way, if you have a question, I think it's going to be easier if you raise your hand in Slack and in Zoom, and then I can pause. But the question is, wouldn't it still be challenging to find an f theta that satisfies integrate? Well, that's the okay. So the question is it not challenging to find an f theta such that this integral is 1? And my point is that we're not going to try to find an f of theta such that this integral evaluates to 1. We're going to start with any f, and then we're going to try to compute its integral and normalize f by that integral to ensure that the final p sums to 1. Yeah, so we start with any f, and then we compute the integral. So this is all going to be quite difficult, but still there's going to be lots of tasks where we're still going to be able to do interesting things without knowing z. And in this lecture, and especially the next lecture, I'm going to show you some learning algorithms, which are some both approximate and exact learning algorithms, which will allow us to learn interesting models of this form. Yair, you also have a question?
Yes, my question was, can you model any distribution with this Gibbs distribution? So I guess like we're not putting any restrictions on f, but could this Gibbs distribution approximate any arbitrary distribution as well?
That's a good question. I think you can probably make that argument because if f of x, if you view the neural net as a universal approximator, I guess that should be right. I think that should follow from the fact that a neural net that's sufficiently large can be a universal function approximator. You could probably make that argument. Yeah. Okay, so as I said earlier, these models can still be interesting for certain tasks. Here, I just want to give you the flavor of a few types of tasks that could be solved using an energy-based model. One task is a form of outlier detection. Let's say that, well, I guess in many of these tasks, the key observation to make is that if we have two samples, x and x prime, evaluating the likelihood at each of these samples does require the normalizing constant. But if we're interested in the ratio, then we don't need the normalizing constant because it cancels out. So let's say that we were interested in an application such as outlier detection or some sort of version of density estimation, then we could apply energy models without having to deal with the hassle of estimating the normalizing constant, right? So the formula for the ratio is just this. We only use the energy, but not the normalizing constant itself. All right, so as a result, many applications such as anomaly detection and also denoising and imputation, for example, let's say that we wanted to find an x prime that is close to another point x that is fully observed, then we could try to optimize this this ratio, and again, we wouldn't have to deal with the normalizing constant. So there are some downstream applications where the normalizing constant is not needed. Yes, question, Marav?
Is there any particular reason that you said that the normalizing constant would be needed in case of anomaly detection? Could I not just do it without the normalizing constant?
Needed. Okay, sorry, maybe I misspoke. I'm saying that it's not needed.
Okay. Okay.
The normalizing constant is not needed. That's the point, right? To estimate the ratio, it cancels out at the top and at the bottom. And then there's also other types of models that we might be interested in, which are these conditional models in which we have labels y and inputs x, right? Let's say that we have, let's say that we wanted to do some sort of conditional estimation, some kind of conditional task. For example, maybe we're interested in object detection or object recognition, or maybe we're interested in assigning labels to elements of a sequence. Let's say we want to do part of speech tagging or something like this. Then we can solve a lot of these tasks, again, without using the normalizing constant. We can solve these tasks by simply optimizing the energy, which is a measure of how good of a fit is there between an x and a y. And we could optimize the energy over y for a fixed x, right? Imagine we wanted to find the most likely set of labels, the most likely set of part of speech tags for a sentence. So we want to classify each word as either a noun or an adjective or a verb. Then that involves only maximizing the energy, not the probability, right? Or the assignment of y that maximizes the probability is the same one that maximizes the unnormalized energy. Therefore, we can reduce the task of finding a good y to an optimization problem over an objective whose evaluation is tractable, and therefore that task can be tracked. The downstream task can be tractable as well. So image restoration is another one. It's an instance of that denoising example that I showed you earlier, and I'll come back to this in just a moment. But my point here is that any time that we have a label y, or not necessarily a label, just a high dimensional object y and an input x, and we want to match them, once we have learned an energy model, somehow we can still match them pretty well by simply optimizing the input, the label y, the variable y. Okay. And again, you might ask yourself, well, this all assumes that I have a trained energy model. Where does it come from? I'll tell you one way of doing this later in this lecture, and then we're going to see an even better way in the next lecture. And also, I'll add that energy-based models can be thought of as a framework that generalizes a lot of types of probabilities that we have seen before. And it's still useful to adopt that framework, even though in general, even though training an arbitrary energy-based model is hard, many of them generalize tractable probabilities, and therefore, many tractable energies, many models are instances of the energy-based framework with a more restricted and tractable energy. And so it's still helpful to know the energy-based framework to reason about these other special cases. I'll answer the next questions. Aren't the integrals for x prime and x going to be different? Thus, the normalization constant is different and cannot be canceled out. So the question is, for different x and x prime, is the normalization constant different or is it the same? And so the point here is that for these 2 points, it is the same. This is really important. The normalizing constant doesn't change if you change the x. The normalizing constant is something that normalizes a probability, which is why it's a function of theta. When you choose a probability function, when you choose an unnormalized probability by choosing theta, that fixes the assignment of unnormalized probabilities all over the space. And then that fixes the normalizing constant. The normalizing constant changes when you change the f of theta, which is when you change the theta. Therefore, it's only a constant. It's only a function of theta, not a function of x. This is why it's called the normalizing constant, because it's constant in x, but it's only a function of theta. Okay, I hope that answered the question. I think this is really important. The normalizing constant is the constant in x. It's only a function of theta. I think that's really important to note. Okay, so we have defined what a what an unnormalized energy-based model is. Let me know if you have any questions so far. And otherwise, I'm going to give you a few examples of classical energy-based models. And these are actually models that have been really important in deep learning and in computer vision for some time. Now they're not. Right now, energy-based models, or at least these classical energy-based models, aren't that big of a deal. There's other ones that are more popular, but I just want to mention these classical models so you're aware of them. Okay, I just want to give a few examples of classical energy-based models so you know what, so you just know them and you're also familiar with these classical results in generative models. One really old type of model, which can be thought of as an energy-based model, is called the Ising model. The Ising model can be seen as a distribution over 2 types of variables, y and x, where x represents some noisy signal that we have observed. You can think of x as being an image. In this case, in this example, I have a 3x3 image. Therefore, x is a 3x3 grid of binary variables. That's what I observed. And I assume that x is some noisy or corrupted version of a true image y. And our task is to recover y given x. In order to do this task, we will define an energy, and that will result in a probabilistic energy model in this form. So what you see here inside the parenthesis is my energy. And this energy involves 2 types of terms. It involves node terms and edge terms. So these are what I call the node terms. And they correspond to every pair of y and x variables in this grid. So the y and the x's, you can think of them as being 2 grids of pixels. We want to infer y from the true y from a noisy version x. And in this energy, I have a sum over pairs of pixels xy and over pairs of neighboring pixels yi, yj. So by yi, yj, I mean that I have a term for each neighboring y here in this grid. Okay, so I have these two sets of terms, and each of these phi i's and phi ij's is just, sorry, psi I and psi ij, it's just some function. It gives me a score. Ultimately, a good model with this form assigns a certain type of score. It assigns a high score. Well, no, I guess here it assigns the lowest because we want to so low energies, or I guess low values of this function are good. They mean we have high probability. So when y and x are similar to each other, this term will be low and it will be high when they're different. And this term will be low when yi and yj are similar and high when it's different. And so as a result, y will have good low energy when it looks like x and when neighboring y's are similar to each other. And that's because in an image, neighboring pixels tend to have similar colors. Right, so neighboring y's should be similar, and then these y and x's should also be similar. So I will choose an energy where similar x and y's are encouraged, and similar y and yj's are encouraged. Given that I have this energy function, I can define the task of denoising this image by maximizing this value p of y given x, and there are efficient algorithms for doing this once I have defined my energy. So this is a way of casting the problem of denoising an image in the framework of energy-based models. Are there any questions about Ising models?
Could you add like a delta function to this to ensure that it doesn't collapse? Like every neighboring pixel is exactly the same as. Because the second component of the loss clearly enforces that all of them should be similar. So maybe.
Yes, so they should be similar, but this term enforces that they're also similar to the x. So the point here is that if some x are corrupted, it could override the value. So if this x is corrupted, it could use the neighboring y's to fix that y. So it could override the x, but it wouldn't do it too often because then it will have bad energy according to the other term. So this is an example of an Ising model. Again, it's just an energy-based model with the following energy, and it's useful for denoising images. Another classical type of model is called the restricted Boltzmann machine. So an RBM, or restricted Boltzmann machine, is a latent variable energy-based model. So I previously derived energy-based models as not having latent variables, but you could just add them to your energy, and that becomes a latent variable energy-based model. So there's two types of variables, x and z. X is observed, z is latent. And the energy that the form of the energy is the following. So it's a quadratic function of x and z. So this is a classical model. It turns out that it can do a lot of interesting, it turns out it's actually surprisingly powerful for a energy which looks at first glance simple. It's just a quadratic. It still can be used to, I guess you can work out the math here. You can show interesting things. So one interesting observation is that there are no visible or hidden terms, right? So if you were to look at the dependencies between the variables, the visible variables depend only on the hidden variables, but not on themselves. So within the set of visible variables and the set of hidden variables, each variable is conditionally independent on, each hidden variable is conditionally dependent on all the other hidden variables given the visible units. So this is interesting. It makes this model more tractable. It's also why it's called a restricted Boltzmann machine. An unrestricted Boltzmann machine would have connections between the hidden and the visible unit. As a result of it being restricted, there are certain learning algorithms which become much more effective for this type of model, and it's still very expressive. There is some math that could be done to show that this has a level of expressivity comparable to a neural network layer. I won't go into these details, but you can derive the expression for the marginal of the hidden given the visible, and the visible given the hidden, and it kind of looks like a neural network layer. In any case, this is actually quite a powerful model. It can be used to easily model digits such as MNIST. Okay, there is a question about the Ising model. In the Ising model, don't we need the actual image Y in the first place? So no, our task in the Ising model is to, so we have X, we don't have Y. Our goal is to get Y. Therefore, we define an energy over both Y and X, and we try to infer Y. Y is the thing that we're trying to predict. And we have an energy over Y and X, and we find the Y which optimizes the energy. So that's the question that was there in the chat. Now, okay, back to RBMs. This is a latent variable energy-based model. They're useful, they're quite useful by themselves, and they're also useful when stacked in layers. And this is what is called a deep Boltzmann machine. This is a historically interesting and important machine learning model. This was probably the first deep generative model that came out as part of the new wave of deep learning. So when the term deep learning was coined, it used to refer a lot to, one famous type of early deep learning model was the deep Boltzmann machine. And this is just a stack of RBMs where we add additional hidden layers on top of an initial layer of visible units. But within each layer, the energy between these two variables is just an RBM. So it's just an extension of the previous energy models to having previous layers. And when we train these deep Boltzmann machines, first of all, it's really not obvious how to train this. I will talk about it shortly, but let's assume we have a way of training it, and I'll talk more about that in a few minutes. Once we train this, these models tend to learn a hierarchy of representations where higher level hidden variables encode higher level concepts, a bit like in the neural net. But again, this is all generative, so there are no labels when it does it. And it can also be useful for generating samples. So here are some samples that were generated by deep Boltzmann machine type of models back in the day. So it's still able to do some interesting, simple generation. And even a single layer restricted Boltzmann machine can, for example, very easily model MNIST. So these models can do some simple generative modeling tasks, and they were state of the art around 2006, 2008, maybe until 2010. Now people don't really use restricted Boltzmann machines, but I think it's still a useful algorithm. It's a useful algorithm to know for historical reasons. Okay, but so far everything that I talked to you, everything that I said, everything that I told you, involved a learned energy-based model, right? So for these motivating applications, the model was learned. Here, when I gave you an example of denoising using Ising model, we somehow had a good energy. In the case of an Ising model, the energy can probably be specified by hand. But for other types of models, for example, these RBM type of models, it's really not clear how you would actually learn that model. And that's what I want to talk about next. So as I said earlier, in general, learning these models is intractable. In fact, even computing the likelihood at one point is intractable because it requires taking the integral. So in the most general probabilistic setting, maximum likelihood learning is intractable. And therefore, we have to rely on approximations. And there's different types of approximations that we're going to see. One type of approximation still tries to do maximum likelihood learning. We're still going to use likelihood as our objective, but we're going to try to approximate it. And there's two main ways of doing this. One way is based on variational inference. That's something that we have seen in previous lectures. Variational inference is a general approach that can be used to approximate many types of it can be used with many types of intractable models. It could even be used with energy models. And the key idea of variational inference is that it reduces approximation to solving an optimization problem where we optimize for an approximate posterior Q. We learn an approximate posterior Q using optimization, and then we work with that Q. That's the high-level idea of variational inference. But that's only one of the two big ways in which approximations are done within probabilistic models. There's a different approach based on something called MCMC, which I will talk about in this lecture. And so this is going to be another broad class of approximate learning and inference methods, but rather than being based on optimization, they're going to be based on sampling. And I'll explain what it means right now. So variational inference was one big family of approximate algorithms. Today, I'm going to briefly introduce another family based on MCMC. And before I do that, I just also want to mention that there are also methods for learning energy-based models that don't rely on likelihood. Another strategy for energy-based models is just to get rid of the likelihood objective entirely, like we did with GANs, and work with a different learning procedure. And that's what we're going to see in the next lecture when we will talk about score-based generative models. But for now, let me introduce MCMC-based methods. So I'll introduce MCMC in the context of a type of model called exponential family models. Okay, here you see the formula for an exponential family. So this is a function where the relationship between the parameters theta and the input x is linear. So x is being featurized with some vector features f, and then the energy is linear in theta and f. So this is actually a very common type of model. For example, a Gaussian would be a special case of this. And this is why I said earlier that a Gaussian distribution could be thought of as a special case as of an energy-based model. And many distributions, many classical distributions in statistics, right? Many of these are special cases of an exponential family. And by extension, they're a special case of an energy-based model. And also some of the other model families that I just introduced to you, for example, Ising models or conditional RBMs. Conditional, I mean that you fix the hidden and you have a distribution over the visible, or you fix the visible and you have a distribution over the hidden. When you clamp either set of variables in an RBM, you also have something which looks like an energy-based model with a particular choice of features X here. So my point here is that many types of interesting probabilities, including many types of energy-based models, are instances of the exponential family. And I'm going to introduce MCMC in the context of exponential family models. So let's say that we have an exponential family model here. As I said earlier, we will still try to learn this model using maximum likelihood. Although in the next lecture, I'll show you that this is not the only way of learning these models. But for now, let's say that we're interested in maximum likelihood. So we can show that the maximum likelihood, which is this, right? It's basically the probability of the data set. Let's say we have a data set D. So the likelihood is the log probability of the data set normalized by the number of data points in our data set, which is the cardinality of the set D. That likelihood has the following form, right? This is the form of my log likelihood. That's just plugging in my definition of an energy-based model. Here, I get this particular expression. So this expression has two terms. It has this term, which is easy and linear. The first term is easy to handle. What's difficult about this likelihood is the second term here, right? This is my log of Z. So this is the really challenging and important term. It's challenging because it involves this So as you can see here, it's log of sum of x, and here this summation is over all the possible x's that I could see. Here I'm just assuming that x is discrete for the sake of this explanation, but it's even more complicated when x is continuous. Let's just say that x is discrete. So here I'm summing over all the possible x's, and so this summation is going to be over an exponentially sized set. It will be intractable, and I can't easily approximate it I can't easily simplify it by switching the log and the x, because I have this annoying summation in the middle. So this term here is what's going to give us trouble, and our goal is going to be to somehow still perform approximate learning and inference while dealing with this term, right? So even evaluating this term is hard, therefore it's going to be even more difficult to optimize an objective function which contains this term. So what can we do? Well, let's just still try to optimize the likelihood using gradient descent. Let's just assume that we can somehow do this, and let's just as a thought exercise, let's try to compute the gradient of this intractable objective that I just showed you. Right, so this is the intractable objective. How can we get a gradient for this? Well, as you can see, and as I just mentioned, there are these two terms. And so this is the first part here. This is the linear part. And that's just a linear function of theta. So if I want the gradient of that with respect to theta, that's really easy. It's just a linear function. So I'm not even gonna spend time on that. That's super easy. The challenging part is this log of z term, but we can still at least try to get a formula for what the gradient of log of z is. And that's what I'm going to try to do here. So if we want to have the gradient for the full function, we have to have the gradient for this term. And with a little bit of derivation, I will post these slides online so you can look at this derivation offline, since we're closer to the end of the lecture now. I won't go through all of the details, but if you look at these few lines, it very easily simplifies to the following interesting expression. So it turns out that the gradient of the partition function is equal to the expected value of the features f of x under the model. Right, so I have a model with parameters theta. The gradient of the partition function is the expected value of the features where the expectation over x is with respect to the distribution with parameters theta. So that's a key fact about any exponential family. And we can use this fact, for obtaining an expression for the gradient of the log likelihood with an exponential family model. The form for that gradient is going to be exactly this. So here I have plugged in my formula for the gradient of the partition function to obtain this term. And then the first term, that's just from the fact that we had a linear model. So, in the objective, it's theta transpose times f of x. Well, the gradient of that function is just f of x. It's just the gradient of a linear function. That's what I use to get the first term. So this is the correct formula for the gradient of the log likelihood, and it has an interesting structure. What's interesting about it is that this is the difference between the expectation of the natural parameters f under the empirical and the model distribution. Right, so if you take this first term here, you can view this as the expected value of f, where the expectation is taken with respect to the data distribution. And this is an expectation over the same set of terms, but with respect to the model distribution. And, you know, eventually I want this to equal 0, which means that these two terms, if I have optimized my model correctly, they will be equal. When the likelihood is optimized, the gradient equals 0. Therefore, the expectation of f under the model distribution and under the data distribution will be equal. And as a result, we have learned the model. And therefore, we can also refer to this type of learning as moment matching. We're trying to match the expected value of the features under the data distribution and the model distribution. We do that implicitly when we perform maximum likelihood learning using gradient descent in an energy-based model, or in an exponential family model. Okay, so this is a fun fact about exponential families. But this still has a problem, right? So this term on the first term here, again, this is easy. This is just the average of a function over our data set. That one we can compute easily. What's challenging is to compute this term. So we have a tractable we have a formula for the gradient, but computing the second term, which I highlighted, that is challenging. And it's challenging because it requires, well, either sampling or inference or taking expected value with respect to p. And that's in general intractable, and therefore computing the gradient is also intractable. So our main challenge is this term, right? This is going to be hard. But it also hints at a way of doing approximate inference in these types of models. Let's say that we could draw samples by sampling X from P in some way. Maybe if we could approximately sample from P, right? Maybe taking exact samples from P is hard, but if we could draw approximate samples, then we could take these samples to get an estimate of this expectation using Monte Carlo. And so the idea of the sampling-based approach to approximate inference is to use this formula and to approximate the expected value by approximately drawing samples from P. Okay, so this is a really key idea. I want to just repeat this again. In probabilistic machine learning, there are two main ways of dealing with intractable probabilities. One way is variational inference, and variational inference reduces inference to optimization. If we can optimize for an approximate posterior, then we can solve our intractable inference task. And here I have defined a second approach, which is based on sampling. If we can, so here we're trying to reduce sampling, we're trying to reduce inference to sampling. And if we can approximate sampling well, sampling instead of optimization, if we can do sampling efficiently, then we can learn this. Well, then we can approximate the expected value, then we can approximate the gradient, and then we can perform approximate learning. Okay, so this is a key idea here. This is really, really important. The idea of sample-based approximate learning is to approximate the expected value in this formula by taking samples from P using approximate methods. Are there any questions about this? If you remember one thing about this portion of the lecture, I think it should be what I just said. Yair had a question.
Yeah, I just wanted to clarify. So Monte Carlo is an approximation of the expectation, and Markov chain Monte Carlo is like an approximation of Monte Carlo. It's like
Markov chain Monte Carlo is a way of drawing samples which will be used for the Monte Carlo approximation of this expected value.
Right, but these samples are themselves an approximation to samples from the tree.
Yes and no. It depends on how you run the Markov chain.
Okay.
If you run it for an infinite amount of time, it's not an approximation. In practice, you have to cut it at some point, so it could become an approximation.
Right.
So, okay, again, at a high level, an important approach to approximate inference is based on sampling. And that's what I just described here. It's really important. One particular way in which we could obtain these samples, right? So now the question is, how do you get these samples X from P? One way to do this is based on something called Markov chain Monte Carlo. And that's what I'll talk about in the time that I have left. And another, a special case of Markov chain Monte Carlo, which I will introduce after if I have time, is persistent contrastive divergence, which is itself an approximation to MCMC. Yeah, okay, I'll just give you the high level idea. I don't think I have time to introduce the method in full, but you can look at my slides later. The high level idea of Markov chain Monte Carlo is to reduce the sampling process to running a Markov chain. So first of all, what is the Markov chain? What is a Markov chain? A Markov chain is a sequence of random variables, which I'm going to denote by S0, S1, S2, and you can think of S as being a state. We start with some distribution over the initial state, and then we have a transition operator that tells us the probability of going to one state when we're in another state. And this could be a visualization of a Markov chain. So we initially start in some state. Let's say we start in 1, and then when we're in 1, well, in this case, we always transition with probability 1 to state 2. Now, once we're in state 2, we can transition back to state 1 with some probability, or with 50% chance. And then with 50% chance, we go to state 3. And then if we ever go back to state 3, then we always go to state 1. And then from state 1, we go to state 2, and then the process repeats itself. Right, so this is a Markov chain can be visualized by a graph with transition probabilities on each edge, and we can transition from one node to the other with that probability. And the crucial aspect of a Markov chain is this Markov assumption, which means that this transition probability is always the same for every step I. So when we're in state 2, it doesn't matter how we got to state 2. Maybe we just started in state 2. Maybe we've been running the Markov chain for 1,000,000 steps. But once we get to state 2, our probability of transitioning to state 3 here is always going to be 0.5, no matter how we got there. This is the Markov assumption. Okay, so it's a process over random variables which has this structure. And the crucial thing to understand about a Markov chain is that a Markov chain defines a probability distribution. When you run the Markov chain for a very long time, you get samples which are drawn from some probability distribution. Okay, what is that probability distribution? Well, let's assume that you have a finite number of states, and the initial state, S0, is drawn from some vector of probability P0. And let's say that I can represent the transition probability, or let's say that I can always write my transition kernel, which is this probability of S mu given I times S previous given J. I can write it as a matrix, right? And then my probability of being in a certain state after T steps, it equals P0 times this transition operator T, capital T, applied lowercase t times. Okay, so if I start with some distribution, some initial distribution over states P0, and I apply my Markov chain T times, I will be in some other state, and my probability over what that other state is will be given to me by P sub T, which is given to me by this formula. So this is just the result of applying the Markov chain many, many times, right? Because it's Markov, I can just estimate the probability of the next step by repeatedly multiplying by the matrix T, right? And then this limit, when it exists, and it often exists, is called the stationary distribution of a Markov chain. It's the limit of this state PT. And you can also prove that it's an eigenvector of this matrix. So this matrix will have a particular, this matrix T that I just defined will in many cases have an eigenvector with eigenvalue 1, and that will be a stationary distribution of this Markov chain. And in practice, what it means is that if I start with some state, in some initial state, and I run the Markov chain for a very, 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 very long time, the state in which I will end up eventually will be distributed according to this distribution phi, which is the stationary distribution of a Markov chain. So a Markov chain defines a probability distribution via this process. The stationary distribution of the Markov chain, which is the distribution of the state in which I will end up if I run the Markov chain for a very long time, that's the distribution that the Markov chain defines. Okay, so a Markov chain defines a distribution. We can check whether a distribution is stationary or not by this formula. So this is actually a sufficient condition. I'll skip this for now. But now the idea of Markov chain Monte Carlo, I want to at least make sure that that I get to mention this. The idea is to create a Markov. So given P, I want to sample from P. So I will create a Markov chain that will generate samples from X. And so the states of this Markov chain will be assignments to the variables of the model, variables in the model. And I will design my Markov chain in a clever way such that its stationary distribution equals the distribution P from which I want to sample. Right? And then once I have carefully designed my Markov chain, I will run it for a while, and then the samples that I will get eventually will be samples from P. And then these samples, I can use them for Monte Carlo integration or for sampling. Just, I could just use these samples. They could be my images that I have generated from the model. So that's the idea of Markov chain Monte Carlo. It's to construct a Markov chain such that when I draw samples from it, it gives me samples from P. Okay, so yeah, typically the way this is run is that I have to define, typically the way an MCMC algorithm works is that I have to define a certain transition operator T, and this is the kind of the hard part. We define the transition operator, and then we run the Markov chain for some number of burn-in steps, and then all the other steps that come later, they will be my my samples. And then if this burn-in stage is sufficiently large, the samples that I will get in step 2 will be samples from my model. Although in practice, I don't really know how long B is, but there are heuristics that people use to define what B is. Okay, so since I'm out of time, so these slides are available after the lecture. I'll just mention that there's a general way of constructing an MCMC chain for the distribution that I want. And this is called Metropolis Hastings. So given any P, Metropolis Hastings, which is on this slide, it gives me a formula for defining the transition operator, which has whose stationary distribution will be the P that I want. Okay, so I'll skip this part. And there's a short proof actually for why that's the case. And a special case of Metropolis Hastings is Gibbs sampling. I'll skip this, sorry. And so now when we apply MCMC sampling with maximum likelihood learning, it gives us an algorithm called contrastive divergence. So contrastive divergence is the learning algorithm is the classical learning algorithm for energy-based models. And so the way it works is that we start with some guess for the parameters of the energy-based model. We run an MCMC chain, such as Gibbs sampling or Metropolis Hastings, to compute samples from the model with a particular theta. Then we use these samples to get the gradient. We take a step of gradient descent, and then we again recompute new samples in stage 1 and so on. So it's basically gradient descent with samples drawn from MCMC. Now, the only difference that persistent contrastive divergence does is that in stage 1, we don't restart MCMC, we just reuse the sample. So we basically, we restart the chain from where the last chain left off, and we don't run it for very long, because if the parameters haven't changed, I don't really need to reinitialize a new chain. Where I left with the old one is pretty good, so I can just do a few more additional samples. So that's persistent contrastive divergence. And this is the classical algorithm for learning models like RBMs or deep Boltzmann machines. Okay, I'll end on this note. We saw energy-based models. In general, probabilistic energy-based models trained with maximum likelihood are intractable, but they still have a lot of interesting use cases. And once we have learned the model, we don't need the energy function, the normalizing function in many cases. And there are also ways of learning these energy models without even using the without even having to compute the constant. So I showed you one approximate way of learning energy-based models using MCMC and contrastive divergence, and we're going to see an even better way of learning them in the next lecture when we're going to look at score-based generative models. Okay, I'll stop here, and yeah, if you want to look at the proofs and the details of the definition of Metropolis Hastings, the slides are online. And yeah, let me know if you have any questions.